So this was our starting point clouds, our starting 2 point clouds. Then we use global registration to find a transformation, so we can actually transform this yellow point cloud to align with the blue point cloud, and that is the results that we can see here that we get from global registration. Hey guys, and welcome to a new video in this point cloud tutorial. In this video here, we're going to talk about global registration in Open3D. So in the last video, we talked about local registration, and we need an initial transformation or initial pose of our object that we want to actually find a transformation and do post estimation of that object in our scene. In this video here, we're going to do global registration, so we can just have an arbitrary rotation and translation of our object, and we want to find that and do post estimation of that object in our frame, or when we're trying to combine different kind of point clouds, how can we find the different kind of corresponding points in the point clouds and then combine them with global registration. But first of all, remember to join the Discord server. I'll link to the description here. You can join the channel, chat about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. And also, if you have some problems in your own projects and so on, I can also help you out if you're a member of the channel. So thank you guys. So we're going to straight into the code here in the Jupyter notebook, where we're actually going to do this global registration. We're both going to look at ICP as we did in the last video. We can actually do refinement after we've done global registration. We're also going to see one of the newest state-of-the-art algorithms within global registration called fast global registration, which is really nice and really efficient when we're talking about doing global registration and have a really high accuracy and precision. But first of all, here we're just going to import our modules here again, Open3D, NumPy, and so on. And we're also going to have this Open3D tutorial, so we can open up this interactive visualization window where we can play around, rotate the point clouds, zoom in and out, and so on. So in this video here, we're going to talk about global registration. So here we can just read that both ICP registration and color point cloud registration are known as local registrations, as we talked about in the last video. So if you want to know how we can do registration in local areas where we actually have an initial alignment or a transformation, then we can actually use that to construct and align different kind of objects into the scene, or just align 2 point clouds when we're combining them together. But here we can see that these methods here, they rely on rough alignment as initializations. So we need this initialized alignment or transformations for our point cloud. This tutorial shows another class of registration methods known as global registration. This is a family of algorithms that do not require an alignment for initialization, as we just talked about. So we can just have arbitrary point clouds, or the 2 point clouds, where we actually want to combine those, and they can be rotated and translated just an arbitrary way. So we don't need any initialization or any initial transformation or alignment to be able to work when we're doing global registration. So the idea behind the global registration is a bit different, but here we can see they usually produce less tight alignment results, and is used as initial for the local methods. So often we're actually doing global registration, and then after global registration, we're trying to fine tune our results, get better accuracy and precision by doing local alignment after we've done our global registration, because our global registration would actually produce a really good output, and then the 2 point clouds will be really close to each other, and then we can just fine tune it by using these local methods as ICP, as we did in the last video, to do the last correction, so we get a really nice and accurate result. So here we're just going to set up these visualization functions as we've done in the other videos, so we can actually display what is going on. So here, to actually be able to draw our registration results, we're just going to pass in the source point cloud, the target point cloud. It could be an object and our scene or something like that, but we can also just have two scenes that we want to actually align to each other. Then we also need to pass in a transformation, so the transformation between the source and the target point cloud, so we can actually align those with this transformation that we pass in here as an argument. So first of all, we're going to have a source temporary point cloud, target temporary point cloud. Then we're just going to point it in a uniform color as we're going to choose. We're going to apply the transformation. As we know, we can just call the point cloud .transform, pass in the transformation that we want to apply to our point cloud, and then we're just going to use draw geometries again here to actually draw our point clouds. So this is just a function, so we can actually draw our results. So first of all, when we're doing global registration, we need to extract geometric features. So here, first of all, we're going to downsample the point clouds, estimate normals, as we've been through in the previous video. So make sure that when you're watching this point cloud tutorial, make sure you watch all the videos from the beginning, because we're taking it like step by step and we're going up one level after another. So after we have our downsample point clouds with voxel downsampling, estimated the normals on that point cloud, then we're going to compute these FPFH feature for each point. So we actually we'll just have a 33-dimensional vector that describes the local geometric property of each of the points in our point clouds. Because when we actually want to match points in 2 point clouds, it is really hard if we're just having, like, for example, 3 features with X, Y, and Z, and maybe a corresponding color or something like that. Then we now actually both use X, Y, Z, the estimated normals, and then also these features here that we are now computing for each of the points together with the color. So we're actually able to find corresponding points in the 2 images, because we want to match those, or like in the 2 point clouds, because we want to match those, so we can actually find a transformation between all those points, so we can then stitch our point cloud together, or like align our point cloud. It could be 2 whole scenes, or it could even like just be having an object, trying to find that object in our scene. And to do that, we need to find matching points in both of the point clouds. So we need these 33-dimensional space or vector here that describes the property of each of the points. And then here we can see that this actually returns points with similar local geometric structures. So we're going to look at like the nearest neighbors and so on for our whole point cloud, matching the points. So here we're going to pre-process our point cloud. We pass in a point cloud and a voxel size. So first of all, again, we're just downsampling our point cloud. Then we're estimating the normals as we've done in the previous videos. And then down here, we're going to call this function from the registration class, compute FPFH features. We're just going to pass in our downsample point cloud, and then we have this algorithm here, KD tree search pyramid hybrid. And then we just pass in a radius here for a radius feature. So this is the nearest neighborhood that we're going to look at. And then we also pass in the max NN, which is just like the nearest neighbors that we're going to look at. So we're going to look at a maximum number of 100 nearest neighbors. Then we're going to return our downsample point cloud, and also our point cloud with all of these features that we have extracted. So we then have a 33-dimensional vector that describes each of the points in this point cloud. So now we have a lot of information about each of the points that we can then use to map between points in one point cloud to a point in the, like the corresponding point in the other point cloud. So here we're going to pass in our input. So here we just read in a source point cloud and a target point cloud, and then they're misaligned here with identity matrix as a transformation. So we're actually just going to rotate it with an identity matrix here, so they're not even close to each other. We won't be able to use ICP on this type of misalignment, so we will need to use global registration, and then we can fine tune that afterwards with ICP and local registration. So here we're going to prepare our data set. First of all, we're just going to run all the different kind of functions here, so we can then run our code. So we're going to enter the input here, we prepare our data set, we set in a voxel size that we want to actually use for our downsampling. We're just going to read in the test data here that is provided by Open3D. So we have these different kind of point clouds that we have from these examples here with Open3D. Then we're going to have our transformation in it here, which is just an identity matrix. We could also just pass in an I here instead. And then we're going to apply the transformation on our source point cloud. So our target point cloud will be the like the original one, and then we're just taking and transforming our source point cloud. Then we're going to draw our registration results, and again here we're just using this identity matrix to actually transform or like show the transformation of our matrix. Then we're going to pre-process our point cloud as I just showed you in the function. We pass in the point cloud and also the voxel size that we want to downsample it with. Then we will get this downsample source point cloud, target point cloud, and also these point clouds with features. So we have all these 33-dimensional features for each of the points in our point cloud. We will get that by calling this pre-process point cloud function. Then we're just going to return the source, target, and these return values here from the pre-process point cloud. function. So all here, we're just preparing our data set, and then we can actually like just call global registration on these return values that we have down here in this function. So we're going to run this block of code. Then we'll go down here and actually like see what is going on. So here we'll just choose a voxel size of 0.05, means 5 centimeters for this data set. And then we're just going to have all our return values here, set that equal to prepare data set. So we're just going to prepare our data set and then specify the voxel size that we want to use. So if I hit shift enter here, we can now see that we're just drawing the 2 point clouds. We have this blue point cloud, which is the original point cloud, and then we transformed the other point cloud that we loaded in. So these are just the exact same point clouds. We just rotated or like transformed it with the identity matrix, so we get this really odd result. And the idea behind this video is that we actually like want to take the yellow point cloud again and find a transformation that can align these 2 point clouds so they're exactly on top of each other. So that means that we need to actually like match those points here, so we can see that the point cloud here is totally flipped around. We wouldn't be able to use ICP or some local registration, because we need to match like these points here in this point cloud to points over here in the blue point cloud, and also some of these points we need to match them over here. So again, this is really important that we have this 33 dimensional vector describing or like having features for all the points in our point clouds, so we're able to do the matching between one point cloud and the other point cloud and find the corresponding points. So now we're actually going to do the algorithm to actually do global registration. So for global registration, we're going to use RANSAC, and we're just going to specify like a number of iterations that we want to run the RANSAC for. We also have some different kind of like pruning algorithms that is implemented in Open3D for RANSAC. We can have like, for example, some correspondence checker based on distance, or based on edge length, or like based on the normals that are estimated. You can just read this here if you want to know more details, or like if you want to know more details about like how RANSAC works. But it's actually just an algorithm to do this global registration and return like, or like reject some of the false matches early on when we actually like using this algorithm to do this global registration. So down here we have this function that we're going to define, execute global registration. We pass in all the return values here from our pre-processed dataset, or like pre-processed dataset function. Then we're going to set a distance threshold here, which will just be a voxel size multiplied by 1.5. Just going to print out some information here, the voxel size and the distance threshold that we set up. Then the only function we need to actually like call to do global registration is this. Inside of registration module, we have registration underscore RANSAC underscore based on feature matching, and these features that we're matching is actually like the features that we got from the previous function as we just went over. Then we just pass in the return values as we've just talked about. We need to pass in distance threshold, and then down here we just need to specify like if you want to do some transformation estimation point to point false. So if you want to do like ICP inside of this function here as well, we're not going to do that because we'll do it after, so we can actually just see the results of global registration, and then we can always do ICP afterwards if we're not like satisfied with our results after global registration, because often we will actually get pretty good results with global registrations or like global registration as well. But if we want like really high accuracy, we will need to do ICP after to actually like fine tune our point cloud. Then we just pass in these puning algorithms based on edge length and also based on distance, and then we just pass in our distance threshold, some values here which is just default values. You can always play around with that for your own algorithm. We also need to set up some RANSAC convergence criteria, so we have a really high number here, and also these are just the values for the RANSAC algorithm. You can go on in here and actually like read what is going on. So here we can see that it defines the maximum number of RANSAC iterations and the confidence probability. So here we will pass in the maximum number of RANSAC iterations. We could probably go with a lower number here, but this is just a criteria when we actually like want to terminate it after convergence. And then here we can see that we have this confidence probability that we need to pass in as well. We're just going to return the results, which will be the results or like the output values from global registration based on feature matching. So we have our results variable, which is the variable that we're going to return when we're calling this execute global registration function. So now we've hit up all the functions that we actually need to do global registration. So now we can just have our results here from our RANSAC global registration method or algorithm. We're just going to set that equal to this function, execute global registration. We pass in all the parameters here that we got from our pre-process our data set or like our point clouds. Then we're going to print our RANSAC results, and then we're just going to draw the registration that we have done. So now I'll run the block code here, and we will actually like that. First of all, we know that we downsample a point cloud with voxel downsampling, doing normal estimations and so on. And then we actually like apply this global registration. And if we're moving the point cloud here around, we can see that all the points here are actually fairly nicely aligned. We can see that there's maybe some disalignment still here in the chair and so on. So it's not like 100% aligned, but we can fine tune that with ICP. But again, compared to results before, if I just scroll up here at the bottom, so this was our starting point clouds, our starting 2 point clouds. Then we use global registration to find a transformation, so we can actually transform this yellow point cloud to align with the blue point cloud, and that is the results that we can see here that we get from global registration. So we can use this for a lot of different kind of things, like for example doing object pose detection, like pose detection of different kind of objects in our scene, or like just align different kind of point clouds. If we have different or like a number of different kind of point clouds that is both rotated and translated in different orientations and translations. So if we just go down here to the bottom again, then after we've done global registration, we can go down and do local refinement. So we're just fine tuning our global registration result. So here, for performance reasons, the global registration is only performed on a heavy downsample point cloud. Because if we have a really large point cloud, it will take too long to do all of these like 100,000 RANSAC iteration. So here we can see that the result is also not tight. So we don't have the like 100% accuracy or like precision. So we can use point to plane ICP to do further refinement to actually like be able to align our point clouds like really close to each other. So we're going to define a new function here, refine registration. Again, we just pass in all the parameters as we do in all the other functions. We're going to set up our distance threshold, and then we just call registration underscore ICP. So we're just doing ICP on our source and target, the distance threshold, and then we just pass in our RANSAC result. So the transformation from a RANSAC result will be our initial guess or like an initial value for our transformation. And the last thing here that we need to pass in is the actual algorithm that we want to use for ICP. And in this example here, we're just going to use point to plane ICP, and then we're going to return the results at the end of this function. So we're just going to run the block of code, and down here we're just going to call the function, store the results, and actually like draw the results as well. So here we can see that we have now aligned our point cloud really nice, as we also saw in the last video. So in the last video we got the exact same results as in this video here, but our initial like transformation was like fairly close to each other. But now we have done global registration, and then we're doing like local refinement to get this really nice and accurate result. We did the global registration on like a downsample point cloud. We can do that to actually like speed up the process, and then we can just do local alignment after local alignment or like local registration after on the whole point cloud that is not downsampled to get these really nice results as we can see that we have. So last thing that I want to show you here, we also get out all the different kind of like metrics that we know. So we have this fitness value. The larger fitness value we have, the better. And we also have the inlier root mean square error that is calculated, and the lower error we have, the better as well. So the last thing that I'm going to show you in this video is that we also have something called fast global registration, which is just a newer algorithm that is used. We can even see like the research paper inside of here. And then we're also going to compare the runtime with the RANSAC-based global registration. And I'm also going to show you with, how long it actually takes to do global registration with RANSAC and then doing local refinement with ICP afterwards. Then we're going to compare the runtime with that with fast global registration, because when we're doing fast global registration, we don't need to do ICP after, because we will actually see that we get really nice results by just using fast global registration. So again, when we're using the RANSAC-based global registration solution or like method, we know that we're doing all these like 100,000 RANSAC iterations, and it just takes a lot of time when we're actually like processing our point clouds, and we can't really use RANSAC-based global registration on really large point clouds unless we downsample them by a lot. So here we're just going to have our input to our registration as in the example above. We're going to set a voxel size because we're just going to downsample our point cloud here as well, so we can better compare results. Then we're just going to pass in all the parameters for prepare the data set as we've done in the previous examples. So we're just going to run this. We will get up our 2 point clouds again, just as in the global registration with RANSAC. Then we go down here and actually set our baseline. So in the code below, we time the global registration approach without local refinement. So here we're just doing global registration and without doing local refinement. Restarting a timer, calling this execute global registration, and then we're just ending the timer and drawing the results. So if I hit shift enter here, we can just see the exact same results as we just got up in the previous examples. But when we terminate the program here, we can see that the global registration took 0.036 seconds. And now we can actually compare this time to the other different kind of methods or like algorithms that are used, also the fast global registration approach. So now we're going to do global registration with local refinement. So now we're both doing global registration, and then after that we're doing local refinement with ICP. We're going to have the same blocks of code here, the same initial point clouds that we're going to try to align. Starting our timer, calculating our RANSAC-based results, execute global registration, and then we're going to do this refine registration with ICP. We're just going to time it and draw the results here again. So when we hit shift enter, we can see that we get the same results as up above. But when we terminate this window here, we can see that this almost took 0.5 seconds to actually be able to run this algorithm here, because we first had to do global registration and then we had to do local refinement afterwards. So it took almost a half a second. We get a fairly good fitness score and also a fairly good error here as we can see. So now we know how long it takes to actually do global registration with local refinement. So now we can try this fast global registration algorithm out. We can see that we have the same input as for the baseline approach. And here down here, we're just calling this implementation of this fast global registration from this research paper. So we're going to define a new function, execute fast global registration. And instead of just doing down here, we just specify another algorithm that we want to use. So all the code here is the same as in the other execute function. Now we're just calling fast global registration option, and then we specify like the maximum corresponding distance, and there will just be the distance threshold. So it'll be the same distance threshold as in the other algorithm. So we actually like to compare all the algorithms together. We're returning the results. I'll just run the block of code. Down here, we're just going to execute or like call this function, time this function, and then draw the results. So now we can see we still get this really nice result as with the global alignment or like the global registration of above. But now we can see down here, it only took 0.168 seconds. So it is almost like 3 times faster to do this algorithm here compared to if we're, for example, doing global registration and then doing a local refinement afterwards. With ICP, we get a really nice fitness score here, really close to the one that we just got up above. That was 3 times slower. We also have a really fairly low like RMS loss here or like error. So this is actually like really good results, and this algorithm here is fairly fast. And if we just compare it to just the global refinement up here without ICP, so if you just want that, like we know up from here from above that it only took like 0.036 seconds. If we just go down to the bottom here again, then we can see that it is actually like still faster if you're just doing global registration compared to if you're doing fast global registration, but then we don't have the same accuracy and the same like low loss because we need to do this ICP or like local refinement afterward. But again, it just depends on your projects, how much accuracy and precision do we need, and also the speed. Sometimes the speed or like the time it takes to actually do this processing doesn't really matter, but if you're trying to do something like real time, you should really take into account the point cloud size, the time it takes to run these different kind of algorithms, and also the hyperparameters or the parameters that we can specify for some of these algorithms. So this is actually like really cool, and we can do a lot of different kind and nice projects with global registration, local registrations, and so on. We're going to create videos about that on this channel here as well. So thank you guys for watching this video here, and remember to subscribe button and bell notification under the video. Also like this video here if you like the content and you want more in the future. I'm currently doing this computer vision tutorial where we're talking about basic image operations, camera calibration, stereo vision, how we can get depth information in our images, how we can convert that into point clouds, do different kind of operations on that, and so on. I'll link to that computer vision tutorial up here, or else I'll see you next video, guys. Bye for now.